Okay, what I'd like to do right now is to solve this particular problem. This is problem 3 of the solution set required for this week. We spoke of this in class on Thursday. It was a combined cycle, which we had air on one side and steam on the other side, connected through then a heat exchanger. And so by knowing the output temperature of the air, we then could figure out the amount of heat that went into the boiling process associated with the steam cycle. And so in this particular problem, we assign an m dot equal to 1 to the left-hand air cycle, and it then determines what value for the mass flow rate is necessary for the steam side. Once we have done that, we then go and observe what the net work was and compare it to 15 megawatts and adjust the m dot equal to 1 on the gas side appropriately. So in this particular case, conditions are all given. And what I'm going to do then is I'm going to launch the test software. The test app is still a vapor power, but it's also a gas power cycle. Instead of selecting this particular steam-only working fluid, we're going to select the case where we can have both steam as well as any ideal gas. And so we spoke of this last time. I'm now going to bring in the various states, and you'll see that by selecting the ideal gas model for a given state, you can then have any ideal gas. If you select a phase change, it will default to water. So in this particular solution, we'll be using the first 7 states will be ideal gas air, and then the remaining states will be water. And so for this particular case, again, I'm going to go ahead and I'm going to bring in my solution. And then we'll just walk through the various states, the solution along with the appropriate device panels. And so I have, let's see what happened here. Let me reopen this again. File, open recent, this one. Hold on. Close that file, don't save. I'm going to open the file back up. Okay, again, I'm going to grab the states and I'm going to copy. What I did was I actually pasted, and so I come back into here. Now I paste those in. I then do a load, and it will then put everything in and come back. And so now all of the various states have been assigned. So again, on the left side, we have the incoming air into the compressor. The conditions are given here, 290 for the temperature of the air and 100 kPa. Notice that I assigned an m dot equal to 1. State 2 is the isentropic work that's required by the compressor up to this pressure. State 3 is the actual work. Obviously, I've changed the enthalpy based on the isentropic as well as the corresponding 80% efficiency of that compressor. I then, state 4 is the high temperature coming out of the combustion chamber going into the gas turbine. And again, it's coming in at pressure 2, which is the output pressure of the compressor. It then, the isentropic work generated by the gas turbine is given by state 5 as it expands to 100 kPa. The actual work is associated with the enthalpy, where I take the H4 and I subtract the isentropic work times a 88% efficiency. And so that gives me the true state 6 going into the heat exchanger. The heat exchanger then expands it or allows it to go to a lower temperature of 420. Okay. Prior to that, the temperature coming out of the turbine was 847. And so the difference in temperature, the difference in enthalpy times the mass flow is then the heat transfer to the boiling of the water. So that's state 7. We now come over to state 8. Now, I have run the problem, and I've already performed the enthalpy balance, and it actually determines what the mass flow rate is in the steam side. And so the purple number there just means that when I brought in and I loaded all the states and loaded all of the device panels, it performed the calculations and came back and said that the mass flow rate must be 0.155 kilogram per second. Okay, so we now go through the isentropic condition through the steam turbine. The M dot is the same as M dot 8. When you load any time and you go and check all your states, sometimes you might not have something that calculated fully, and you notice that I just hit calculate, and it then recognizes that it used this. So this is the isentropic output to the turbine as it expands to 8 kPa. The actual condition is a different, higher value of enthalpy, higher by a 90% efficiency based on the isentropic work. And so, again, the M dot 10 is the same as M dot 8. And so that is our, our output to our condenser. And then our condenser runs through and it comes out of the condenser at a quality equal to 0 at the pressure 9, which is the pressure of the of the condenser. We then have it go through. This is the pump, and we see that the pump has an isentropic work going back up to P8, and that value here corresponds to a certain enthalpy. We then calculate the actual work at state 13, and again, in this case, we see that the pump was an 80% isentropic efficient pump. And so again, we do the same process we did before. We're increasing the enthalpy by a little bit more than what it would have been if it was isentropically pumped up. And so that's our state 13. So now we have all of our states. We then go to our device panel. Our device panels, we start off, the first device panel is the device panel that corresponds to that closed heat exchanger. Okay, that closed heat exchanger, and what we know about that closed heat exchanger is the air coming in at state 6 flows through and comes out at state 7. In state 7, we knew the temperature of the air. State 6 is what we knew the temperature coming out of the gas turbine. And so that's the one stream, and that's at 1 kilogram per second. And then this, this other side corresponds to what came in at state 13 out of the pump, went through, and this to state 8. And so that's the boiler, the pseudo boiler associated with the water side, the steam side. And so it's from the solution of this heat exchanger, this closed heat exchanger with the two streams, with no heat transfer and no work going out or in, that it calculated then the magnitude for a mass flow rate of 1 kilogram per second. It figured out what the magnitude of the steam flow rate had to be in order to balance this energy equation. Okay, device 2 then was the compressor over on the air side and the amount of work that it needed. Device 3 is the combustion chamber over on the left side and how much heat had to come in to raise the temperature of the air. Device 4 was the turbine, the gas turbine, and how much work it generated as the air expanded down to 100 kPa. And then we had the steam turbine over on the right side as it went from state A through to the actual state 10. And this is how much work that the steam turbine generates. And then we had the condenser, and this is the condenser going from 10 to 11 and how much heat is rejected in the condenser. And then we have device 7, which is the pump, the steam pump, the feed water pump, and it takes the state 11 to state 13. And so that's the actual state associated with the pump. And we see a little bit of work that's being required. And so that ends up all the device panels. Now when we go to the cycle panel, it has now taken all of the heats that had to be supplied, and in this particular case, the only heat that we had to supply was the heat in the combustion chamber on the left side for the air. We then also added up the two powers generated by the two turbines, and we subtracted the amount of power that was required by the pump, which was small, and we added to that the power for the compressor over on the air side, which is much greater. And so we see that the net work is then equal to 440 kilowatts. Okay, the thermal efficiency is calculated based on what the net work was divided by the heat transfer. And we see in this particular case that the thermal efficiency of this combined cycle is a little over 50%. However, to finish up the problem, we recognize that the actual net work of this combined cycle due to 1 kilogram per second of fluid was 0.44. And we want this to be 15. And so I'm going to copy that number. And I'm now going to go back to the state panel, all the way back to state 1, where I assign a mass flow rate equal to 1. And so when we assign this equal to 1, that gave us 0.44 megawatts of output power. And so we want this to actually be 15. And so I'm taking the 15 and dividing by that 0.44. So that's the mass flow rate that must be passed through the air cycle. And the corresponding mass flow rate will be determined for the steam portion, and that will then answer our question. So I put that in, I do a super calculate, and now I can go back to my state panel, and I can go back to where it generates the MDOT for 8, and we now see, okay, that should have gone up. Let's see what happened. Okay, I'm going to go back. I'm going to do a super calculate. Okay, upon super calculating, if I look at the cycle panel, the cycle panel should represent a higher value there. Okay, so let me go back to my state panel, back to where I changed the state 1. Okay, it didn't take that particular number. Maybe I forgot to divide by or hit the return key. And now it took it, it's green. I do a super calculate. I go back to the cycle panel, and now this should show up as 15. And it does. Okay, I hit the calculate, and so now this is 15. What we can do is go to the I/O panel, and in order to output, we can put in equals m.1, and we see that that's 34 now instead of 1 kilogram per second. And we can also put in m.8, and that would then be the 5.288. And so those are our two values of mass flow rate that are necessary to answer the problem. So 5.288 and 34.06. And so with that, and we go back and we say, have we answered all the questions? Okay, we have the thermal efficiency was a little over 50%. If I went back here and went to the cycle panel, we see it's 50.66 is the thermal efficiency. This is not affected by the mass flow rate, okay, because it's just the ratio of two numbers that are proportional to the mass flow rate. And then we go back and we say what is the mass flow rates of the air and the water, and we see that we printed those out. And what's the heat transfer to the combined cycle? Well, the heat transfer to the combined cycle would be this number right here, 29.6 megawatts. Again, that was the only place where we had to purchase heat to put into the system. Okay. We did not have to do anything here. This was all internal. This is where we put the heat in, and we then obtain 15 megawatts of power out. And so we go back to our here, and we see that this 15 megawatts divided by 29.6 is where we get the 50.66% thermal efficiency for this particular system. And that then answers the question. It also showed us how that we could go through and in a combined cycle, we could have some states that are associated with air acting as an ideal gas, and some states that are associated with water as a phase change fluid, how we can tie the two together with heat exchangers, closed heat exchangers, how the problem automatically keeps track of all of the works and all of the work outs and all of the work in, whether it's a compressor or whether it's a pump, and it keeps track and determines the thermal efficiency of the combined cycle. So with that, I'm going to turn off the recorder.